So, good morning, good afternoon, good evening to everyone. It is a pleasure to be back at the WISE webinar. My name is Baba Ahmad Mala, and I'm a PhD candidate at Beihang University. Today, we are going to dive into our lecture, Introduction to GNSS Receiver Architecture, its core functionality, and cutting-edge application. The journey from space to screen. Our title is given from signal to solution. So what we actually mean by from signal to solutions is from the signal we receive from the constellation in the space to the solution on our phones. A signal actually is generated by a satellite orbiting almost from 20,000 kilometers above us. It travels at the speed of light. It enters a tiny antenna. So when we take our phones, the old phones you see it has an antenna that you can, it works like a radio that has an antenna. But modern phones and then the phones we are holding on our hands now, you cannot see the antennas, but there is an antenna inside the mobile phone. So my journey started at after my secondary school education. I went to Sharda University and I studied computer applications. After I was opportune to come to China to study information and communication engineering. During my master's, I specialized in computer vision and how images work. So at Beihang University, I am doing space technology application, specifically GNSS systems application. Last year, when I was invited to the webinar, I presented a paper. It was a published paper about evolution of GNSS technology, which is an introduction. So with this opportunity that I got to present today's lecture, I will deep dive into GNSS receiver. So GNSS receiver is part of the GNSS, which is like the backbone of the GNSS, the chip, how it works. Some of my technical skills include Python, MATLAB, the GNSS signal analysis, and I have served in a Nigerian communication satellite for 1 year, and I'm a member of the IEEE publication, and then Nigerian communication, and then Nigerian Computer Society member. So why GNSS receiver? Why are we talking about GNSS receiver? So GNSS receiver, from the continuation of the last lecture to today's lecture, I'm going to talk about the signal, and then to see why did we choose this particular topic. So I broke it down into 3 parts. One of the reasons is a continuation of our last lecture, and then the title I have given to signal to solution we are having, and then the GNSS receiver matters globally. It works within our phones, within the autonomous vehicle, that is its application. It works in the farms, in drones, in power grid, everywhere there is GNSS receiver when we notice. So that was the motivation of choosing this particular topic. And then I would like to share what I have learned over the year and what I have drafted within the paper and submitted for publication. I would like to share with you guys. So the content of our lecture here, we are going to introduce the GNSS overview. What is GNSS? The constellation, receiver architecture, the signal architecture, its cutting-edge application, and then the challenges and future trends. GNSS overview. So GNSS is a collective term for all satellite-based navigation system, providing autonomous geospatial positioning with global coverage, including GPS. GPS is the most popular one. We keep hearing about GPS. Then we have GLONASS of Russia, Galileo in Europe, Beidou of China, and then Navigation IC of India, and QZSS of Japan. So GNSS, what it does is interested in three parts. Is interested in positioning, navigation, how do you navigate from A to B, and then timing. That is what makes the GNSS what it is today. So how GNSS works, there's thing we call trilateral tracing, which is a satellite broadcast signal containing precise positioning plus a timestamp of an atomic clock accuracy. I could remember in the UK, there was during coming up of a clock, a prize of £20,000 was given to anyone that can come up with a clock, the fastest one, and then one of the scientists during that time came up with a solution for the clock. So timing is so important that before, just like we contest for certain things now, a lot of people are doing their research, studying how to make the clock we are benefiting from it now, the timing system. So receiver measures signal travel time. It multiplies by speed of light. It computes satellite. It has an intersection space around 4 satellites. It solves the 3D position plus receiver clock. Navigation engine outputs include the position, the velocity, that is the Doppler, and then time in UTC updated to 100 Hz. These are the 6 constellations of GPS, GLONASS, Galileo, and Beidou of China. The architecture, the second part of our presentation, we mentioned that it's an introduction of the GNSS receiver, its architectures. So what made the architecture of the GNSS receivers? One includes carrier signal, the PRN code, navigation data, and yes, navigation data, which are the navigation messages. So carrier signal, this is a radio frequency wave carrying the information, the L1, L2, and then all the frequencies, which those frequencies helps to better provide an accuracy. It gives a better accuracy. And in the PRN code, these are the pseudo-random noise, which is a unique 1023-bit gold code sequence identifying each satellite. It identifies each satellite. It repeats every 1 millisecond, which is used to calculate the signal travel time called the coarse acquisition, or the code for the GPS L1 civilian signal. These are for the civilian use. I have the military one as well. Next is the navigation data. This picture, you can see what I'm actually doing. I'm trying to get a message using my Beidou receivers from the space. So this is also the third architecture of the GNSS receiver. It helps in navigation data, that is navigation messages. Pseudo-random region measurements, we have the code pace as we discussed earlier, and then the carrier pace. This is the difference between the code pace and then the carrier pace. In carrier pace, we have the PRN code is almost or always 1023 bits, that is it, which is equals to 1 milliseconds. And then in carrier phase, we have which counts the number of carrier cycles from satellites to receiver. These are some of the difference. Here we have a chip which is 300 meters in distance. In carrier phase, we have the GPS L1 carrier, which is 19 centimeter. The pseudo range, the true range plus receiver clock plus of aero and atmospheric delays gives the pseudo range. Why the pseudo is called? Because the receiver close is imperfect. That's why its name is called pseudo. In carrier phase, the algorithm include the RTK, the precise positioning. For pseudo range, is basically used in the clock, and then here for carrier phase is used in survey, precision farming, and autonomous vehicles. This is the architecture of the GNSS receiver. You can see the antenna here, and then we have an RF front end, which goes into the processing channels, and then the processing channels process the data. After processing the data, now has from the processing the data, it goes to solution, and then here to the measurement weight, it goes back and forth, and then here we have the local oscillator, which references and gives the frequency. It's like a synthesizer. It's synthesized. From there, it goes to the RF front end. And in the next slide, we are going to explain each of these. So here is the RF front end. So when you deep dive into the RF front end, it has the satellite signal. It has the band phase. It has low noise amplifier. It has a mixer. It has an ADC sampler. The satellite signal arrives, which is an extremely weak, like 20 dB below thermal noise. The band phase filter removes out of the band interference, and RFI passes GNSS frequency band only. So today's lecture is actually very technical. I made it in such a way to be more theoretical, but GNSS receiver is all about calculation and then the figures and then the equations. So next we have the mixer, which shifts to low intermediate frequency IF for processing. You have the ADC sampler, goes from analog to digital. It helps in quantization. Next is the baseband processing, acquisition and tracking. I'm going to talk about the signal acquisition. To the signal acquisition, it finds a 2D space which searches over 32 PRN code, pseudo range codes, multiplied by the Doppler shifts. Next, it makes a correlation, which is a reverse local PRN code copies in time. The correlation peak is equals to satellite that is found. Then next is the cold start. It does not include any prior information, which goes into searching all the codes plus Doppler beams, which is at the range of 30 to 60 seconds. It has a warm start of Almanic store, which is fewer beans to search. For signal tracking loops, It continues to follow acquired signals with high precision. It has the DLL, the PLL, the FLL, the tracking bandwidth, channel count. The DLL, that is the delay lock loop, what it does, it tracks the PRN code, which output the pseudo range with meter level precision. For PLL, it tracks carrier pace and it enables centimeter level carrier measurements. For the frequency lock loop, it tracks carrier frequencies and then it compensates the Doppler shifts used in initial clock. For tracking bandwidth, which a beta noise rejection is equals to the narrow bandwidth, and then it tracks fast vehicle dynamics. A fast vehicle dynamics equals to the wide bandwidth. This is the engine of the navigation, the positioning, velocity, and time computation. How it works is, it first of all collects the pseudo ranges. Next, it computes the satellite positions. It applies the error correction. It solves position equation. This is the technical part of it. And then how it's conducted, first of all, you collect the pseudo ranges, which is track satellite measured in PRN code of time travel multiplied by the speed of light, and it gives minimum of 4 satellites. You have to have a minimum of 4 satellites to collect the pseudo ranges to have a better or accurate result. Next, it computes satellite positioning. You have to decode a premise from navigation messages, the message you receive. Then you calculate the satellite position, the distance, then at time of the signal transmission using Keplerian orbital mechanics parameters. This is the formula you have to use to compute the satellite position. Next, then correction of an error, whether it's ionospheric error, tropospheric error. Using a particular formula, then you correct the error. If it's an ionospheric error, it has its own way of correcting. If it's tropospheric error, it has its own way of correction. And then next you move to solve the position equation, which a nonlinear system is equals to pseudo range linearized into an iterates weighted least squares plus an extended Kalman filter tracks over time and computes velocity via the Doppler. This is the next part. In the next part, it includes error sources in GNSS. Here we have said how to apply the error correction. So some of the errors here we explain what are some of these errors. So the errors include ionospheric delay, tropospheric delay, satellite clock error, ephemeris error, multipath error, receiver noise. Ionospheric delay typically is an error the higher the figure, the higher the error. It charged particles in ionospheric slow signal or dual frequency receivers, which eliminate this. Single frequencies uses Klobuchar model. Tropospheric delay, its error is less. It's between 0.5 to 2 meters. It is gotten from the water vapor, and dry air refract these signals. So in a GNSS reflectometry, the signals that hit the water, these are some of the tropospheric errors. Next, we have the satellite clock error. mostly is below 1 meters. Atomic clock drift corrected by polynomial coefficients broadcast in navigation messages. So for satellite, clock error is less, and then for ephemeris error is between the range of 1 to 3 meters. Is predicted orbit imprecision. And then next is the multipath error. The multipath error is also high, is between the range of 1 to 5 meters, which are signals from urban canyons in a tall building or within the city. These are some of the errors that is gotten from building or from the ground reaching the antenna. And then next we have noise. Its error is also from the range of 0.3 to 1 meters. Includes thermal noise in hardware. It can be improved using an ADC bits, using filtering, and using carrier phase averaging, which reduces the impact significantly. Next, we are going to talk about GNSS augmentation. The GNSS augmentation, I'm going to talk about the satellite-based augmentation, differential GNSS, the real-time kinematic, and then precise point positioning. The satellite-based augmentation examples is the UWSE, the IGNOS of Europe, and the MSARS of Japan, and the Gagan of India. It works using a ground reference station to monitor GNSS satellites. So each country has its own augmentation base. It's based in that particular country. For differential GNSS, it's a fixed reference station with known position. It computes correction and broadcasts to nearby moving receivers. Next is the real-time kinematic. How it works, it uses a carrier phase measurement plus fast data link between base and rover to resolve integer ambiguity in real time. A precise point positioning takes a different approach. It uses a global network to create highly precise satellite orbit and clock corrections, which a single receiver can use to achieve decimeter level accuracy without a nearby base stations. The ultimate test for GNSS, let's say this technology in action, starting with the most demanding application, self-driving cars, that is self-driving cars for in order for it to know how to navigate safely, it needs to know its position with the lane level accuracy. The accuracy must be good, between 5 to 10 meters. If it does not have a lesser accuracy for self-driving cars, it's almost not important because it involves lives and then accident can happen. So the recipe for the lane accuracy or the lane level accuracy is to achieve a lower centimeter error. How they do it, first they use a GNSS RTK plus an IMU, that is GNSS plus IMU. Next is the IMU provides a continuous motion data. The more it moves or it tilts front or back or moves sideways, it gives a data which bridges gaps when the GNSS is lost. in tunnels or in urban place where the network is not good. So what happens is when the self-driving cars is in urban canyon, it could not receive the signal well. It will start to have an error. So if it's having an error, accident can happen. So that is where the IMU comes into play. So it helps in that. It helps in an extended Kalman filter blend these sensors seamlessly without any problem. Next is the safety and robustness. Safety is paramount. System like receiver autonomous integrity monitoring and used to detect if any satellite is giving faulty data. The vehicle use available constellation. Since we have multiple constellation, it will choose one for its maximum satellite availability. But the urban canyon remains a big headache, a big problem, with around 25 to 30% of the sky visibility. Solution involved a 3D CT models, even tighter integration with the IMU and wheel speed sensors. It will have a multi-system problem. So this is one of the challenges here. It has the application of autonomous vehicle. This particular application we are talking about is for the autonomous vehicle. We mentioned how it works. It uses the lane level position. When there is an error, the IMU helps. It uses vehicle to everything communication device. It carries all the communication device that could help him, but the urban challenge is a big challenge. That's why you can see in a Tesla, if you have seen a Tesla car, how it works is they actually have the map, a 3D map of the entire city. Most of the cities that function, so they have the 3D map of that particular city, so it could navigate on its own when such errors occurs. Since urban challenges of 30%, most errors is caused by that. Most of the cities now, due to urban planning, the city has long skyscrapers, and the ultimate taste. You can proceed. Okay, the ultimate taste for GNSS. Let's see this technology in action, starting with the most demanding application, that is the autonomous vehicle. For a car to drive itself, it needs to know its position with lane level accuracy. And lane level accuracy, which the standard is 5 to 10 meter in our phone GPS, it can tell if the car is in the left lane or in the right lane or in the ditch. The recipe for the lane level accuracy is received when we have an arrow below 10 meter. It uses a sophisticated technology. First, they use the GNSS RTK. The GNSS RTK. Next, they integrate with inertial measurement unit. That is the IMU. That is the IMU fusion. The IMU provides continuous motion data. It bridges gap when GNSS is lost in tunnels or in urban canyons, while GNSS corrects the IMU's drift. An extended Kalman filter blends this sensor seamlessly. Next is the safety and robustness. Another benefit is the safety and robustness of the systems called the receiver autonomous integrated monitoring, which is used to detect if any satellite is giving faulty data. Vehicles also use available constellation, multi-constellation for maximum satellite visibility, and yet the urban canyons remain the biggest challenge. One of its challenges is it has a challenge of 25 to 30% of the sky visibility. It blocks the sky that the receiver within the autonomous vehicle could not get a correct navigation data to navigate within the city. Next in our application is the precision agriculture, UAVs, and timing. Transforming agriculture, we have to revolutionize other industries too. Another industry include the UAV drone navigation, which is interchange between the, precision agriculture. The UAV could be used for precision agriculture as one of its technologies. In precision agriculture, RTK is guided through a tractors which can auto steer within 2 centimeters, allowing for perfect straight rows 24 hours a day. It could work all day. This maximizes wasted seeds, fertilizers, and fuel. Farmers nowadays use GPS maps to apply chemicals only where needed. It's a technique called the variable rate application, and it creates yield maps that show the productivity of different parts of a field, reducing input cost by 10 to 15 through targeted precision application. The brains for the UAVs and drones is called a GNSS navigation sensor. The sensor it has here is critical functions hold include the position hold to hover steadily and return to home. In return to home, that is its place of departure to the destination, it could navigate back to where it started using a post-process kinematic. What it does, it creates a 3D maps and models from an aerial photos. So the 3D maps and models from an aerial photos is called photogrammetry maps, which is essential for construction, mining, and agriculture as well. The invisible backbone of infrastructure. The most crucial part include the 4G to 5G base station. Uses a GPS discipline oscillator to stay perfectly synchronized, which allows to hand over calls seamlessly from one tower to the next. Power grid use GPS time to synchronize sensors across hundreds of miles to monitor grid stability, and stock exchanges timestamp every transaction to within 100 nanoseconds. GNSS is silent, precise heartbeat of modern infrastructure. That's why most of the time we are more focused on the some of the technologies that is known to those particular sensors, to those particular infrastructures, but we tend to ignore the GNSS, which is the heartbeat of most modern infrastructure, whether it's robotics, precision agriculture, UAVs, autonomous vehicle. Without the GNSS, it could not function. The challenges in GNSS: jamming, signal jamming, the low-tech threat. With a $20 to $50 device, you could disrupt a UAV worth thousands of dollars. Mostly criminals use them to block fleet tracking, but they can also accidentally jam ports or airports. The solution is resilience using multi-constellation. How you can overcome this is using a multi-constellation null steering antennas, IMUs as a backup. Next, in the problem of GNSS includes spoofing. It is even more dangerous than the jamming or than the jamming. So in how signal spoofing works is instead of blocking the signals, a spoofer broadcasts fake, slightly more powerful GNSS signals, tricking the receiver into calculating a false position. The receiver has no idea it's being deceived. This has been used to hijack ships. Countermeasures are cryptographic, like Galileo's open service navigation messages, authentication, which digitally signs the signal to prove it's an authentic. So they come up with the solution to use a cryptographic authentication to ensure it's authentic before it goes to the position. Next is environmental challenges and systematic challenges. We have talked about the ionospheric scintillation earlier, but we will dive deeper here, which causes by solar activity. It can make the signal fluctuate rapidly and even disappear, completely disappear. This is particularly severe near the equator. So some of the equator countries include Nigeria, there are also practical challenges. It is very challenging to come up with the ionospheric delay or ionospheric errors, but the solution mostly done is using multi-sensors to overcome such challenges. Future trends in GNSS technology. So where is GNSS heading? First, we would like to say GNSS is heading towards many sectors, and currently these are some of the trends. Include deep learning, which helps to acquire signals that are extremely weak or within a noisy environment. And the neural networks are being used to train, detect, and mitigate multipath errors that is caused in urban canyons. And the AIs can make the receivers more smarter and more adaptive. Integration with other technologies. GNSS could be integrated with 5G. This is where most of the research papers, when you look at the research papers, this is currently what is mostly going on. Integration of 5G and then the GNSS. Perhaps the most exciting is the low Earth orbit, the satellite navigation. The signals are 1,000 times stronger than the GNSS. So their signals are much stronger. Adding a navigation payload to this communication satellite could provide robust, high accuracy positioning even in challenging environments. New hardwares, new applications within a multi-frequency is becoming the standard consumer phones, dramatically improving urban performance within the urban environments. Those applications, our mobile phones, our self-driving cars, are navigating smoothly. We are also seeing the development of chip-scale atomic clocks, which are exploring entirely new application like the GNSS reflectometry. So GNSS reflectometry is an entire new sector which is booming within Japan, China, and many developed countries, where they use the reflected GNSS signals to measure ocean wind speeds, soil moisture, and ice thickness, turning a communication system into a global remote sensing tool. The future of GNSS is not just about better positioning, it's about more resilient, intelligent, and multi-phase technology. Next, we are going to talk about the summary of our lecture, what we could take away from this lecture. As we come close, we started by expanding our view of GNSS from just GPS to a rich ecosystem of global constellation serving billions of devices. We have billions of mobile phones serving the global market, and then the receiver role and capabilities. We saw that the receiver is the critical piece of engineering. The receiver is very critical for the technology we are using. It's a sophisticated pipeline that takes a signal buried in noise and extracts a precise fix. We learned that the accuracy isn't a single number. It spans orders of magnitude from 10 meters with basic code paste to 1 centimeter with carrier paste techniques like the RTK. Impact and obstacles. Some of the impacts and obstacles we explored is transforming the entire industries from the way we drive and farm to how we fly our drones and how we synchronize the power grids. We have also acknowledged the significant challenges, the threat of jamming, spoofing within the urban environments and spheric issues, which are critical areas of research. But mostly, the future is fusion. Where we are heading mostly is the fusion. Within all those challenges, if we could take the GNSS on its own, AI, 5G, IMU, LEO, make it a multi-sensor fusion, then this would lead us towards what? Towards resilient, ubiquitous, and centimeter accurate navigation for everyone and everywhere. Thank you very much for listening to this lecture, and thank you for your attention. It was a privilege to share this presentation of Introduction to GNSS Receiver Technology with you. I hope this lecture benefits you. And then if you have any question, we want to discuss anything, I'm open for it. Thank you.